I'm back. Okay.
Hi.
I don't know what's wrong with my internet this morning. Never mind that there's a million things running on it. An iPad, 2 computers, a wireless printer, 1, 2, 3 TVs, you know, whatever. Never needed so much technology at one time in my life. What was I saying? Okay, I've got sort of a view of you guys right now, and I'll try to share my stuff again. Let me make sure somebody else is trying to get in. There's Sarong got bumped off too. Let's get her back on. What I was asking was, Damaris, you there now?
Yeah, I'm here. Thank you.
Here, are you okay? You here?
Yeah, I'm here.
Look like you got bumped off. Okay, so the Tacoma River Bridge was a bridge that was built across a river that runs off the Puget Sound in Washington State, just to the left of Seattle. And the engineers that were working on that bridge didn't take into account something when they built it. Has anybody seen this picture of a bridge collapsing over a river? It was.
Yeah, you've showed me before.
Yeah, Haley, you saw it in class. Yeah, it's the bridge after it was built, all of a sudden started sort of wavering. If you looked at it from the side, it would be looking like a sine curve, for example. And when the amplitude of the sine curve got too high, I mean, people were trying to figure out when this would happen, and they could walk down the center line and keep their balance, but the edges of the bridge were sort of twisting back and forth. The amplitude of the sine curve got too high, the whole thing collapsed. Right? It just collapsed in the water. And what they did not take into account was some winds that were coming down from the north that would funnel down the Puget Sound into this narrow space where this bridge was. And what it did was set up a vibration in the bridge. And when the vibration got set up, it was sort of like a spring going back and forth and getting further away every time. And it just tore it apart. They since rebuilt it. I think they probably rebuilt it twice, not because the second one failed, but because it got obsolete. But anyway, it's a great video. I'm going to see if I can get it up for you guys to show you when we talk about springs and amplitudes of curves and so forth. But other than that, you might want to look online. I'm sure on YouTube is one of those vintage videos of that thing. All right, let me try to share the screen again here. All right, here we go. All right, anybody questions before we start or either get bumped off again? Okay, so what I want to talk about today is a different kind of DE. It's not too hard to solve. It takes a long time to get the process, but like with method of undetermined coefficients, it has and all of them, it has a characteristic equation, and actually the characteristic equation is very similar to what we did before, but it turns out that it is a DE that does not have constant coefficients on it. What it has is variable coefficients. So instead of 2y double prime minus 3y prime plus 5, we'll have some function of x that's not a constant as those coefficients. Those DEs are much harder to solve than constant coefficients. I mean, we've pretty much looked at the two methods that are the method of undetermined coefficients and the method of variation of parameters that can be used to solve those with constant coefficients. Most DEs with variable coefficients, not constants, are solved using series. Now, some of you have had series and some of you haven't. So what I'm choosing to do, I often spend 2 or 3 days on series, just sort of telling you what it is and using that. But I'm chosen not to do that because we're pushed for time a little bit. Plus, it's something not everybody's had. I mean, if you had Calc 3, or maybe you took calculus when we had 4 calculus courses, you had it in Calc 3. If you took Calc 2 recently, it was the end of Calc 2. But I'm not going to deal with series, but there are some equations that have variable coefficients that are can be handled fairly easily. And one of those is something called a Cauchy-Euler equation. Okay, so what I want to do right now is define what I mean by this thing called a Cauchy-Euler equation and figure out how to solve that. If you look at this sort of generic form of a DE, what we're going to look at here is something of the form a sub n x to the nth, a sub n minus 1 x to the n minus 1. Those are all the coefficients on the derivatives and the function. Now, what you want to know about this is that this time all those ANs right there, all these things right here are constants. But in addition to the constants, you've got a power of x in front of the derivative, all right, as part of the coefficient on whatever derivative that is. Now, the important thing in the definition of a Cauchy-Euler equation is that the power on n here, the power on x, is the same as the order of the derivative. So, for instance, if this was a third derivative, that would be an x cubed. You can see that happening here. If it's an n minus first derivative, the power on it will be n minus 1, and so on. If it's the first derivative, it'll be x to the first. Y, of course, is kind of the 0th derivative, so it's sort of like an x to the 0 here. It'll just be the constant. The only one of these things that'll have just a constant on it, if it appears, is the last one, which is y. So that's what we mean by a Cauchy-Euler equation. So as with so that's the big they're easy to recognize. So you won't have any trouble recognizing them if they're in a pile of things because they have this very specific form. What we're going to do is the same thing we did with the method of undetermined coefficients to begin with. We're just to look at a second order and see what it takes to get a second order generic equation solved, and then we'll extend from there to higher orders. Now, one of the things you're going to have to be careful of here. A lot of times we paid attention to on what interval was this solution good. Well, when we had constant coefficients, we really didn't have to worry about that. But if we put this thing in standard form, in other words, if you divide by ax squared here, there's going to be an x in the denominator. Okay, so if the ax squared is gone here, it'll be bx over x squared, and that'll just be b over x. So x can't be 0 when I put it in standard form. What that says is that when we look at these things, the solution will be good on the interval from minus infinity to 0 or 0 to infinity. You can't include 0 in that, all right, because of this variable coefficient on the front. So x can't be 0 there. Okay, so what we're going to do first is talk about how do we solve one of these things that's homogeneous. Okay, and it turns out if we can do this, we can solve a non-homogeneous one because we're going to go back and use variation of parameters. Okay, so the non-homogeneous part is okay. We can do that. We just need to figure out how to solve the homogeneous part of this. And remember that we're going to need that. Our solutions are still going to look like this. YC plus YP. So a complementary solution. In other words, the solution to this one, all right, plus however we get the particular solution. So we're going to work on how to get the complementary solution in this one. Okay. Now, just sort of a place to start. It looks like you're starting at random. When we did constant coefficients, we needed a function as a solution that sort of repeated itself in its derivative, so it would all subtract out and only differed by a constant when you differentiated, and that was E. So when we were looking at all the members of the fundamental set for my constant coefficient equations, you'd always get e to the 2x or e to the 3x, depending on what your roots of your characteristic equation were. That's not quite the way it's going to work on here. Because we have this x squared and we have these powers of x, we're going to make a guess that the solution is going to be some form of x to a power. So that when I differentiate that, I get more x's to powers, and maybe I can get them to drop out in the equation and equal 0. So that's the big ticket item here. That's our guess, and that's what's going to end up working. So we're going to try to find out how we would find the solutions of this if the solutions indeed, and they do, look like that. All right. So I'm going to do what I did before and what we've done in a lot of different situations here. I'm going to take the derivative of this thing, and it's just x to the nth power. The first derivative will be mx to the m minus 1. If I take the m minus 1 down again to get the second derivative, I'll have x m to the minus 1, sorry, m times m minus 1, x to the m minus 2. I keep taking away a power. If you keep looking at if you look at the pattern here, you're bringing down m 2 times here. Well, there's a second derivative here. The last thing you take away here is 1. It's 1 less. So this power right here, this will be m minus k plus 1 and x to the m minus k. Anyway, if you keep taking those derivatives, you know what you're doing. You're adding this. The next one would be m times m minus 1 times m minus 2 x to the m minus 3. So that's what we're doing. We're just taking simple power rule derivatives. Okay. So what I'm going to do is take that sample derivative there and put it into this second order thing and see what has to be true to make this true. So if I look at this, if you look at it carefully, guys, and see what I've done, I had to scroll down, but the coefficient was ax squared. The second derivative was m times m minus 1 times x to the m minus 2. So this piece right here, all of this is the second derivative. There's the bx right here, and the first derivative was just m times x to the m minus 1. The guess that we made, y, was just x to the m. Okay, so all I did was take this guess, plug it in there. Now, if you look at this thing, one thing you'll notice is that it'll have an x to the m in every term. This is a lot like when we had an e to the x in every term, or e to the ax, or whatever it looked like, or e to the mx. We pulled it out. So I'm going to pull it out here and look at what's left. Literally, it's just a little bit of algebra here. This, and this are left. If I'm doing a second order equation, you can tell this is going to be a quadratic here. If I multiply out, I get am squared minus am plus bm plus c. And if I put these two terms in the middle together, I get b minus a to the m, or times m. So I do have a quadratic. It's a quadratic where if you think about the quadratic formula, the a term is a, but the quote b, the coefficient on m, is b minus a, and then you just have a constant c. Now, in the end, that's going to be important for me to use as a shortcut for something I want to do.
Dr. Harris.
Question, anybody so far?
Yeah, on the second step, did you divide by x squared?
Over here.
Yeah, like what did you, like that, hey, I see where you plugged
Oh, no,
it
oh, good question, Haley. I should have said that. It's an x squared, and you got an x squared to the m minus 2. So when you combine powers there, what do you get? If you add your exponents, what do you get there? What happens with the 2 and the minus 2?
They're eliminated. Could you add them?
Yeah. Look at this. It's x squared times x to the m minus 2. And then when you add the 2 together, you're going to get, the 2's will cancel out and you get x to the m. I'm just doing a little algebra there, okay? Notice the same thing happened here. This was x to the first times x to the m minus 1. And the 1's cancel, and you get x to the m there. And then there was nothing to do here. All right, so I just combined those two terms right there, okay? And in this case, over here, I did x times x to the m minus 1. And so that's the 1, add the powers, you'll get x to the m in that case. That's actually going to happen no matter how high your powers go. For instance, the third derivative would have had an x cubed and an x to the m minus 3. So the 3 and the minus 3 would have gone, and I still would have had x to the m. Haley, do you understand what I'm doing?
Yes, I saw it.
Okay, all right, good. Okay, so just doing that algebra there, I pull out that x to the m, and I end up with this. This is the characteristic equation for a second order, DE, Cauchy-Euler equation. Okay, so I'll get Allison back in. Looks like all the internet in the world is glitchy today. So there it is. There's the characteristic equation. And the only way this thing can be 0, we don't want that to be 0, because it needs to be a member of the fundamental set. That's what we've guessed. That's what our fundamental set things are going to look like. And you can't have 0 in a fundamental set because you wouldn't have linear independence then. But this thing has to be 0 right here. So what we've got to do now is solve that quadratic. And it's very similar. It's not the same exactly as the quadratic we solved for method of undetermined coefficients, or when we initially learned how to do these homogeneous equations, but it's still just a quadratic. All right, so let's take a look at this. So our characteristic equation for this second order thing looks like that. Okay. Now, it's a quadratic. So we're actually going to have the same 3 cases that we had before. When you've got a quadratic, you can have 2 distinct real roots. Now remember, what this happened before is if you got the roots of your equation, when this was something with constant coefficients, if we got our roots were 2 and 3, it would have been e to the 2x and e to the 3x. Okay, that's going to be different here because it's x to the roots. But we're going to solve it in a very similar way. So 2 distinct real roots, we'll call them m1 and m2. Then my solutions are going to look like y equal x to the m1 and y equal x to the m2. All right, let me give you an example. If I take this dE right here, it is definitely Cauchy-Euler. Notice the x squared and the y double prime there. The x to the first and the y prime, and then there's no x in there, x to the 0 and whatever. It's the original function, there's no derivative. Now, what I want you to note here is that if you look at this thing right here, the a, the coefficient right there is 1. Remember, I was sort of looking at, when I looked at a generic, I was looking at ax squared, y double prime, plus bx, y prime, minus c, or plus cy equals 0. What you notice here is that the a is 1 and the b is minus 2. Now, I'm going to go through this thing, and it says that characteristic equation is am squared plus b minus a to the nth plus c equals 0. But just to show you again what I'm doing, I'm going to plug in these derivatives here and show you that that's what I get for this specific case. So if I put in y double prime, it looks like this. If I put in y prime, there's that. If I put in the function, it looks like that. I proceed to multiply everything out. Actually, again, and these two, this and this combine to be x to the m, and this combine to be x to the m, and there's an x to the m. So when I pull x to the m out, I've got m times m minus 1 minus 2m minus 4. So my characteristic equation for this one is that thing right there. Okay. Now, what I want you to notice about this, and we're going to shortcut this, and I don't mind if you shortcut it. Because it takes a long time, particularly if you're doing one that's more than a second order dE. Look at the coefficient on this. According to what we generically said the characteristic equation was, we said that coefficient should be b minus a. Well, look at how we identified from the beginning. We identified b is minus 2 and a is 1. B minus a, minus 2 minus 1. In this case, minus 2 minus 1 is minus 3, and that's what you got right there in that characteristic equation. Okay, so we'll practice that again because we're going to do several more of these. But the point is, ultimately, after we kind of get the idea of why this is working here, I'm not going to do all this again. If it's a quadratic, now you have to do it if you have something of higher order. But if it's a quadratic, this coefficient on m in your characteristic equation is always going to be this b minus that a. So b minus a. Okay, what do we do with the characteristic equation? Well, the only way this thing right here is going to be 0 is if that thing is 0. So I'm going to solve that. It'll factor in this case. So I wind up with, that'll be m squared, and then of course minus 3m minus 4 right there. So the roots of my characteristic equation here are m equal minus 1 and m equal 4. What that says is that the roots that will go with that will be x to the minus 1, because our proposed root, remember, was x to the m, x to the minus 1, and x to the 4th. Okay, So let's look at what we've got there. We got x to the minus 1, C2, our complementary solution, our general complementary solution is going to be C1x to the minus 1 plus C2x to the 4th. You can show that these things are linearly independent. They do form a fundamental set. They will never be 0 anywhere except at 0, but since we're not even considering 0 in here for reasons I talked about a minute ago, this coefficient right here becomes 0, so we sort of bump that out. We can find that those are linearly independent. Okay, so that's what it looks like. Question anybody on that? So the distinct roots are the easy part of it. Okay, we okay? All right, let's go to the next case. The next case is repeated roots. So in other words, maybe my characteristic equation looks like this. Okay, and we would have a m in it usually, but if I factored that, I'd have a repeated root of -2. So I really only get one m1, all right, in that case. And if you remember what we did when we were doing constant coefficients, if I got a repeated root and say the repeated root was -2, my fundamental set looked like e to the -2x, and the other one was x e to the -2x. Okay, that's what happened when we had constant coefficients. Clearly not what's going to happen here because they look like this. So we want to figure out what happens when we have a repeated root in this situation, in the Cauchy-Euler situation. Okay, so so let's recall something about having repeated roots, particularly in a quadratic. If you look at the quadratic formula, you're going to have repeated roots where on your quadratic, what's under the radical in the quadratic formula is equal to 0. You will have repeated roots when that's equal to 0. But here's what the quadratic formula would look like in this equation. Now, I don't want you to get confused because of the b's. It's unfortunate that there's a b in the original quadratic formula, but they're certainly not going to change that for a DE course. If you want to solve this quadratic right here, the a part is still a, hence you would have 2a down here. But the b part, the coefficient on m, I would need to take minus that. So instead of just a b, where I would, if I were looking at an ax squared plus bx plus c, that's what it would be. But my quote b here is b minus a. So it'll be minus b minus a over the 2a plus or minus, and this will become 0. All right. So that's something that we can know if we have repeated roots in this case. So that if I turned it around, let's see, let's distribute that minus through there. That would be a minus b over 2a. Now, I'm going to use that as a piece of a little bit of a proof next. But that's, if we were solving the quadratic equation and we knew that the coefficient was b minus a, that's what would go there. So it would be minus that coefficient, whatever it is, over 2a. What's under the radical would be 0. Okay. So here's what I'm going to do. I know one root here. I know that one of the roots here is y1 is x to the m1. But it's repeated. So the question is, what do I do to get another solution that's linearly independent there? I'm going to go back all the way to section 4.2. It seems like a long time ago, only like 4 or 5 sections away. But 4.2 was that section called reduction of order, where if we had a known solution, we could find another solution, another linearly independent solution. This is part of like the bonus that I asked you to do. And I said, if you've got one solution, we'll call it y1. You can find a second one by using this formula right here. You guys had a homework on that. So if you've got a known solution, you want to find another linearly independent solution, you can do this. Yeah, let's remember what we had to do. We didn't memorize that formula. All we showed it was linearly independent using the Wronskian in one of those bonuses. But the first thing we had to do was put the equation in standard form. That's extremely important here. If we don't put this in standard form, there's not much we can do with it. Putting it in standard form means to divide by ax squared. So I've got to identify a p, guys, and the p came from something that was in standard form. So before I can use this formula, I got to divide by ax squared. So bx over ax squared, x over x squared just leaves me with an x in the denominator. And I get b over a, y prime, c over ax squared, y equals 0. Okay, so I now have it in standard form. All right, question anybody? So I'm kind of setting myself up to see what a second solution looks like here. Okay, so if I look at this thing, p is b over ax. So there's the p. Remember, standard form looked like p y prime plus q. I'm not actually going to use the q for this part of it, but that would be the q. Okay. And I think Tiara or somebody asked me yesterday, if you put it in standard form, there's a coefficient of 1 there. The answer is yes. It's the same idea here. You need a coefficient of 1 there. So I'm going to use this formula and put everything I know into it and see what happens and see if I can get a second linearly independent function. I should be able to, because we proved that y1 and this y2 right here were linearly independent. So here's what I'll do. I'll use the y1 that I know, which was x to the m1. And then I'll put my p in here. It'll be integral e minus, my p is b over ax. The y1 that I know is x to the m1, and I'll square it. At this point, let's go from here. In this one right here, x to the m1 squared is just x to the 2m1. Raise the power to a power, you multiply. If you look at this thing right here, I'm going to pull out the b over a. And there's a minus in front of there, so it's minus b over a. And I'm left with 1 over x inside that integral. And the integral of 1 over x is log x. So that's how I got from here to here. Pulled out the minus b over a, integrated 1 over x, and got log x. Now, in reality, that looks way nice. I can make that look way nicer. Because what I'm going to do is use some properties of logs to simplify this.
Dr. Harrell, how?
Yeah. What?
You said you pulled out the what?
I pulled out, see this minus b over, see this b over a in here? That was part of my p that I put in there. Okay, so that was my p. I put in b over ax, and then I just pulled out the b over a. It's just a constant. I pulled it outside the integral.
Okay, because it's a constant.
Mm-hmm.
Okay.
Yeah, it's just my coefficients on the characteristic equation, basically. Or actually not the characteristic, but the dE. So when I pulled it out, I was left with, so here's the interim step here. It's minus b over a times the integral of 1 over x. Okay. And when I did that, I had minus b over a, and the integral of 1 over x dx is log x. Okay. Everybody okay with that? Now, we want to get rid of e's and logs anytime we can, particularly when they're working so closely together here. We've got a property of logs that says if I've got this constant right here times the log of x, I can bring it up as a power. Okay, we've done that many times. I bring it up, I wind up with this. I wind up with this thing right here. So I just brought that minus b over a, and it became a power on x to the minus b over a. Working in reverse, it would come down. You got the same thing. The nice thing here is when you apply e and the natural log to each other, they undo each other. They are inverses. So what I have now is x to the m1. They undid each other, so I'm left with just this part. X to the minus b over a, so that's what I get right there. And what I get in the bottom is just x to the 2m1. Okay. Question, anybody? You okay to that point? Now, here's the nice part about this. I actually know what m1 is if this is a repeated root. I'm gonna swing back here a minute, guys, and something I said a minute ago. Because that was the b coefficient on the characteristic equation, and because it's a repeated root, this thing is 0. So I found out that m minus 1 was just a minus b over 2a. Okay, that's what we were looking at there. That's just from the quadratic formula with that as a coefficient on m. So if I put in a minus b, whoops, where'd it go? Yeah. A minus b over 2a, that's my m1. Actually, guys, and there's a, well, what I get there is the 2. There's the 2 from the square. Actually, I didn't put in a minus b, I just put in minus b minus a. It's the same thing. The 2 came from the power. There's the 2 right there on that. The m1 is this thing right here. So that 2 was this 2. All right, that was the fact that I squared the bottom there. And then this whole piece right here that I've got in the circle is the m1. The 2's cancel. All right, the 2's cancel there. What I end up with is x to the minus b over a and x to the a minus b over a. So that's where I made the sign change right there, guys. Minus b minus a is a minus b. The 2's are gone, and so this is over a. Now, you may wonder why I'm doing this, but things simplify nicely, actually. So I'll stop there for a second. Questions, anybody, about where I got anything going, basically going from here to here? You okay with that? Okay. So what we've got is something that looks better, but I can make it look even better. I'm going to divide this out right here, this power right here. If I divide it out, it'll be 1 minus b over a. So that's all I did in this step. 1 minus b over a. Just a into b there. I'm then going to break down the powers, break down that difference on the powers there. That's just the same thing as x to the first times x to the minus b over a. And x to the minus b over a was precisely the term that I had in the top. I'd been dragging that along for a while. Okay, so what happens at this point is that those two things cancel. That all comes from the fact that we got repeated roots and how the quadratic formula behaved. Now, if I cancel those things, I'm left with xm1. Now remember, I'm still working with that formula about creating a second linearly independent solution, but I've gotten down to this point. xm1, integral of 1 over x. The integral of 1 over x is log x. So that tells me that my second linearly independent solution in a repeated root looks like that. It looks like that. Remember how we had, in a repeated root with constant coefficients, we had maybe e to the x and x e to the x? Now it's x to the m minus 1, x to the m minus 1 log x. So that's what my fundamental set looks like. Okay? You can show they're linearly independent. All right? You can show they are linearly independent. I'm going to do, there's 2 bonus points. I'm going to give you some bonus points here. The first one of those is to show that those are linearly independent. We know that we're going to show things are linearly independent by using the Wronski, and knowing that x can't be 0, I think you can show that's pretty easy. Okay, so I will use that for bonus points again. You can hand it in with your homework on Friday. Okay, do I want it separate from the homework? Let's do this separate from the homework. So hand this in to me by tomorrow. Okay, this won't take long, I don't think. It's just it's going to be a Wronskian. And a 2x2 Wronskian. So separate that from your homework, guys, so it'll be easier for me to grade. And also, when you're handing in your homework, make sure your name's on it, and on this one you'll just say bonus. Okay. All right. And if possible, I don't know what's, and so Ron, this is when you send me your homework, is there a way to send it in one document instead of 3 sheets at a time? There may be somebody else doing that too, but I just remember that yours was like that. Are you still there, Saran?
Yeah, I'm not sure.
Okay. Are you doing it with a scanner?
Yeah,
on your phone?
Yes.
It's a scan all 3 of them at a time, and then I think it'll put, and then hit done after they all 3 go in, and I think it'll all go into one document. Okay, and if it doesn't, it's fine. It's just that I have to. And if you don't do that, it's okay. But what I want you to do on your pages where you scan them, name one of them page number 1, page number 2, page number 3. I end up kind of looking back and forth to figure out what order things are in. Okay, but I mean it's okay. But I think you can get it all in one document. Okay. All right. Question anybody about this? So let's do an example. All right, so that'll be just a couple of bonus points. And again, those are just added into your points to get you closer to whatever the 100% total is. Okay, let's do this one. So I've got 4x squared, second derivative of y, plus 8x, first derivative, plus y equals 0. That's a Cauchy-Euler equation because of the matching power here and here. The order of the derivative and the power on x are exactly the same. Okay. Now, I said we weren't going to do this again, but just to remind you one more time, we're putting in those derivatives. That would be the second derivative, the first derivative right there, and crank all this stuff out, do the algebra here. X squared times x to the m minus 2 would be just an x to the m, and so on. I keep going, I get this. Now, on your homework, and this is not due until, I don't think I've put the Cauchy-Euler is probably not due until next week sometime. But you can take a shortcut. What we knew is that this coefficient right here ended up being b minus a. If you look at the original DE, the b was 8 and the a was 4. So 8 minus 4 is 4. That's what that's going to be right there. Okay. So, and notice that the other 2 are just the coefficient here and the coefficient on the function. That's 1 right there. So it's a y double prime plus b minus a, y prime plus c. So these 2 just pick up right from the equation, and this one is b minus a. So you're good to go on that shortcut. Okay, everybody okay with that? Because that'll definitely save you some time on this. All right, let's look at how we're going to solve it then. We know our characteristic equation looks like this. When we factor it, we get 2m plus 1 times 2m plus 1. That's equal to 0. M is minus a half, and it is repeated. The solution to the homogeneous part of the system, or the homogeneous, not system, but the homogeneous DE here, is x to the minus 1/2 and log x, x to the minus 1/2. Okay. So, so guys, let me ask you a question here before I get started on, well, before I decide what I'm going to do next. If you remember, if I had repeated, suppose I had repeated roots of 3 in one of the ones we did before, not Cauchy-Euler, but constant coefficients, then my fundamental set would look like e to the 3x, x e to the 3x, and what would the next one look like? I mean, I've got to have 3 pieces because this is a third order here. It's got repeated 3. What would the next one have looked like, guys? I got 3 repeated roots. One of them's e to the 3x, x e to the 3x. What did the next one look like?
X squared e to the 3x.
Yeah, it looked like x squared. Okay, I saw 2 people popping up at the same time. All right, this is x squared e to the 3x. So what we did was add a power of x every time. Let me tell you that the extension on the Cauchy-Euler equations to higher than second order or higher than 1 repeated root does the same thing. If you've got a root, the first piece of the fundamental set is x to the m1. If that root is repeated once, it'll be x to the, I should have put an m1 on that, x to the m1 log x, like the one we just had. If it's a root of multiplicity k, or if it were 3, it would be x to the m1 log x squared. We bump up the power on the log x. Looks exactly the same, except you're bumping up the power on log x. So if you've got multiplicity k, you keep bumping up that power on log x until you get to k minus 1. Okay? All right. Let me, I want to scroll that. I'll let you take a second to write that down. Let me scroll. Has everybody got it before I go on? So that's one of the things they write sort of in the text in the book. Let's see if I can find one like that. Let's see. I don't see one like that. But I'd tell you what, I am going to do an example of a non-homogeneous one here. Okay, I'm going to skip over something that I had in here to begin with. Now, so we've talked about distinct roots. We've talked about repeated roots. The one thing I hadn't talked about is complex roots, and I'm going to save that for Friday. Okay. I want to look at what happens if it's non-homogeneous, so I can review with you variation of parameters, because that's the homework that'll be due Friday. So suppose I had one of these Cauchy-Euler equations, and it look like this. So it's non-homogeneous. I cannot solve this by method of undetermined coefficients. It simply doesn't work if I don't have, that method does not work if I have non-constant coefficients here. Because, I mean, if it did, we would make a guess at this, and we might use the method of undetermined coefficients, where we'd make a guess about a polynomial times e to the x or whatever. But the things that are similar here are I do have to find my YC. So once again, let's look at what our YC is going to be. It's going to be 1, for our characteristic equation, it's going to be 1x squared. It pulls that A is the same there. It pulls that 3. This minus 4 is B minus A. All right, so minus 3 minus 1 is minus 4, and there's your characteristic equation real quickly without putting all the derivatives in. When I factor that, I get roots of 1 and 3. So my YC is that. These are distinct real roots. I don't have any problem with repeated roots or anything there. Now, let's review what variation of parameters said. Now, one thing you want to be very certain of, or you will get the wrong answer. When you use variation of parameters, you have got to divide by this leading coefficient here. When it was a constant, it didn't look like much of a problem. It's not much of a problem. When it's a non-constant, when it's a variable, you still have to do it. So the first thing I'm going to do, to remember to do when I'm using, anytime I'm using variation of parameters, is put it in standard form. Once again, that means you're going to have a 1 right there. So when I divide this whole thing through by x squared, that just gives me y double prime. 3x over x squared just gives me 3 over x, of course, with the minus out front. 3 over x squared this. The right-hand side, if you put divide by x squared, this x to the 4th over x squared is going to become an x squared. That's why this changed from that, because I divided by that. And you can see what an effect it's going to have on your solution when you use variation of parameters, because this is part of what I put in my determinants. It's part of what I put in my determinants. Okay, so let's review variation of parameters for a minute. Okay, so here's what variation of parameters said. That's this function right here on the right-hand side, this non-homogeneous equation, that is my f of x. Once I divide through it, it's by f of x. Before it's called a g of x, but you divide through by something, it's a different function. Okay? So variation parameters said this. Take the members of your fundamental set, which in this case were x and x cubed, and take the derivative here and the derivative there. In other words, find the Wronskian. That's what that thing was all about. Okay? And what we are finding here is u1 prime. And I'll remind you why we need u1 in a second too. So there was u1 prime. W is equal to that. That's easy. The determinant of that is 3x cubed minus x cubed is 2x cubed. That's pretty easy. And you get the same thing in the u2 prime in the bottom there. Because the Wronskian goes in both of those, in the bottom. We're using Cramer's rule. This is the thing I talked about last time. Cramer's rule says if you want to find the solution in the top, you replace it with 0 f of x. Well, there's my f of x. Remember, I divided it through by something, so there's my f of x. If I had put that original thing in here, that 2x to the 4th e to the x, I would get the wrong answer. I have got to divide through by x squared. I cannot emphasize that enough, because everything from here on is going to be wrong if you don't divide by that. So if you want to find u1 prime, in that determinant in the top, you put 0 f of x. So I put in this thing right here. And what goes in for the second column is the same as the second column you had below. Okay. When I find that determinant, that's 0 minus 2x to the 5th e to the x. Just only thing that combines are those powers of x there. So 0, somebody was doing a determinant wrong on this on one of their homeworks. It's this way, top left to bottom right, and then minus top right to bottom left. When I look at those two things over each other, I get minus x squared e to the minus x. That's something I'm going to need in a minute. That's my u1 prime. Okay. If I go to the next one, u2 prime, Wronskian's in the bottom. First column remains the same. Second column gets replaced with 0 f of x. Again, not hard to find the determinant here. This times this minus this will be 2x cubed e to the x over 2x cubed that I got from below, and I just get e to the x. That is my u2 prime. Now, I want to remind you before I scroll up, because why am I doing this? Because the yp, if you remember, has the form this. u1, y1, plus u2, y2, where y1 and y2 were the members of the fundamental set up here, the x and the x cubed, which we got from solving a Cauchy-Euler equation, homogeneous. So I need to find U1 and U2, but it's not hard because I have the derivative of U1 and U2. So what I'm going to have to do is just integrate. Let's put it right there. So to find U1, I'm going to integrate minus x squared e to the x. Now, I got a little lazy here. I think this is about, this is close to 11:30 last night. I said, you know what? And there are formulas I can find this by. That's parts twice. And so I just wrote down what is. I would try that and just get it, if you're a little bit rusty on parts from the last time we did it, try it again. If you do it one time, it'll reduce to a single power of x. You do it twice, you'll be able to integrate it. I don't need the plus c, but that's my U1. For the pain I went through to do this, the integral of U2 prime, or the U2 prime was e to the x. So the integral of e to the x is just e to the x. That one was really easy. So my final answer here takes those things right there and puts the YC and the YP together. So the total general solution here looks like the YC, which we knew was this, because those were the roots of the characteristic equation of the Cauchy-Euler equation. And then U1, Y1, well, here was my U1, that thing we had to integrate parts, do parts twice. Y1 was X, that's one of the members of my fundamental set. And then plus the U2, which was just e to the x, times the other member of the fundamental set. See, this was my Y1, this is my Y2. So that's what I get there. Now, guys, let me point out to you that this is the YP, right? All of this stuff right here is the YP. It has no parameters in it. The C1 and the C2 go with the fundamental set. Usually this thing can be simplified. So all I did was multiply everything out here. And then I found out that a couple of these things drop out. If you multiply this, it'll be minus x cubed e to the x, and it'll drop out with that plus x cubed e to the x. The final YP here, the final y, whole thing, final y, looks like that in a simplified form. Okay. Now, if I had any initial conditions, I would just plug them in like I usually do. I mean, whatever, if I had something like y of 0 equal 3 and y prime of 0 equal 1, I'd plug in 0 to this whole thing and maybe find out what a C1 was or a C2, or get two of them and figure it out. I would then take the derivative of this, not too hard because these things are easy to take the derivative of now, and plug that in. I'd have a system of equations and I could find C1 and C2. So that's never any different, but you need this whole thing to do that. All right, questions, anybody? Okay. I know you think I'm relentless, but I'm getting ready to let you go early, but I need to say one thing. I assigned the homework in this section so that it included all the work on Cauchy-Euler equations. I have not dealt with complex roots. So if you start doing some of the homework on this and you come to one with complex roots, just realize that you've done part of the work already, and on Friday, we'll talk about what you do with a complex root. So you guys have distinct real roots and you have repeated roots. And if you have any mixture of complex, forget it, don't worry about it. We'll do it on Friday, okay? So homework, get the rest of your homework. You get the homework to me on undetermined coefficients. That was those 4 things that had the solution in the back. And oh, by the way, I've copied all the pages from the book, so everybody should be working on the same problems, and the solutions are back there. Remember, I gave you odd problems so you could see if your solutions were correct. Okay, so work on those 4 problems, get them to me sometime today. I'd like to try to grade them tonight so I can get them back to you. And then the next thing that's due is variation of parameters on Friday. And this is what I just did. It's a good review of that. All right, any questions?
Bonus due tomorrow, correct?
The bonus is due tomorrow. Yeah, let's just do the, guys, that won't, if you sit down and look at those things in your, in a Vronsky, and it won't take you 10 minutes, okay? Maybe, if you check it over 2 or 3 times. So do that one. And I have another bonus for you tomorrow too that has to do with the complex roots, okay? All right, so send that to me, and unless somebody has any other questions, I'll see you on Friday. Are we good? All right, see you later.
Thanks.
Bye-bye.